Okay, we are back. I'm now going to describe to you how each and every one of these spectrums is produced. Now what I need you to notice, and remember this, remember, you pass a white light source through a prism, you get red, orange, yellow, green, blue, indigo, and violet, okay? And remember, the sun is a white light source. The sun is also a star, so it also emulates a black body. So in this diagram you see up here, it says it's a hot black body. Well, the sun is hot. It acts like a black body. But at the same time, what I need you to think about when you see this is that this hot black body, which is a star, and in our case we're going to talk about the sun, it's also a white light producer. So make sure you put that down in here. It's a white light producer, okay? Now, we're going to take a look at the continuous spectrum first. It's like I said before the break, it's kind of the most worthless spectrum. It doesn't really tell us a whole lot. It's mainly used for training purposes, okay? Teaching students about spectrum. And so what I have here is the sun. I got a white light source. I pass it through the prism. What happens when you pass white light through the prism? The prism refracts the light based on frequency, and you get red, orange, yellow, green, blue, indigo, and violet. Boom! Look at that. Red, orange, yellow, green, blue, indigo, and violet. Okay? So, what is this telling me? It's telling me my source of light is a white light source. Well, good duh. Almost everything in astronomy is a white light source, okay? So for us, yeah, I know that already, okay? But if I get the rainbow of colors, I know I'm looking at a white light source, okay? In this case, the sun. These lines, guys, are showing you the source of light. Now let's take a look at the next one, the absorption spectrum, okay? A little bit more complicated. You'll notice the line is coming all the way back to the sun, all right? So I've got a white light source. The white light is passing through the prism. Boom, I'm getting the rainbow of colors here. But there's something about this one that's different than the continuous spectrum. There are lines missing. In other words, there are very specific frequencies of light that are missing. Why do we call this the absorption spectrum? Because those frequencies of light have been absorbed by something. Now there is a difference between this path of light and this path of light. You can see it. You won't say it, but you can see it. This path of light is passing through this cloud of gas right here. And it's this cloud of gas that is absorbing those frequencies of light. And remember what I told you, each element has a very specific spectrum to it, okay? And so when I look at this spectrum, and I only know this because I've been doing this for 40 years, when I look at this spectrum, that is the hydrogen spectrum, okay? And so these lines and those frequencies of light are missing would be the hydrogen spectrum. So that tells me something about this cloud of gas. If the frequencies of light that are missing are those for hydrogen, what is this cloud of gas? Tell it, say it loud, be proud. Yes, that's correct. Hydrogen. The cloud of gas is made of hydrogen. And I know this because it's the hydrogen frequencies of light that are missing, okay? Now remember this, white light through a gas will produce an absorption spectrum. And the frequencies of light that are missing will tell you what the cloud of gas is made of, okay? Now, let's take a look at the third type, the emission spectrum. What is emission? That means giving off. So this would be a spectrum that's produced by something emitting light, okay? But because you don't see the rainbow of colors, you don't see that here, it's not a white light source. So it is something that's emitting very specific frequencies of light, and it's not a white light source because you don't have the entire rainbow of colors here, okay? Now, if you look at this one here, you'll notice that the line for the light path starts here at the cloud of gas. So what is this telling you? That the source of light is coming from the cloud of gas. This cloud of gas is now emitting specific frequencies of light, okay? So, I've got the cloud of gas emitting light. It passes through the prism. When it does that, it shows me this very specific frequencies of light that are being emitted by this cloud of gas, okay? Now, if you were to take this spectrum right here and put it over this one right here, these lines, this orange, green, blue, indigo, and violet line, would fit into those empty spaces right there. So, when I look at a spectrum like this and I get very specific frequencies of light, from those very specific frequencies of light, I can now tell what the object is made of that's emitting the light. And in this case, again, hydrogen. Okay? Hydrogen cloud of gas, I knew that from this spectrum. But if I didn't have this spectrum and all I had was this, I could still tell by the very specific frequencies of light that the object emitting the light, in this case a cloud of gas in space, is actually hydrogen. Okay? All right. How can a cloud of gas produce light? I'm not going to go into a lot of detail on this. I'm simply going to walk you through it with words. Okay? When you take an object like a cloud of gas like this, we know this cloud of gas is made of hydrogen, so it's made of hydrogen atoms. When you take a cloud of gas and you add energy to it, you excite the atoms. Now, what are the different forms of energy that we have? Well, I've got electricity coming out of my wall sockets. That's a form of energy. Heat is a form of energy. Radiation is a form of energy. Okay? So these are some forms of energy that we run into every day. Now, I don't have a giant wall socket out in space that I can plug this cloud into. So that's probably not where the energy is coming from that is exciting the atoms in this cloud. More than likely, it is radiation from a star. So radiation from a star, remember, radiation has energy to it. Radiation is hitting this cloud of gas and it is exciting atoms, okay? Guys, atoms do not like to be excited. They don't. The energy is exciting them. They will de-excite. When an atom de-excites itself, it produces certain frequencies of light depending on what the atoms are. So anytime you take hydrogen and you excite it, when a hydrogen atom de-excites, it will emit these very specific frequencies of light. Okay? Now the next couple slides go into more detail about this. Skip those slides. Just understand. An object like a cloud of gas will emit light by itself when you excite the atoms. When the atoms de-excite, they emit light at very specific frequencies. Okay? All right, so I'm going to, if I can get my it's not working. Why? Because it's a piece of junk. There, beat on it. It'll work, right? Nope, still won't work. Okay, let me go get the mouse so I can do this. Okay, I'm not going to talk about this slide just yet. Well, this is the slide I'm wanting to skip. This is telling you how light is emitted. I'm not going to talk about the Doppler shift right now because I want to show you how stars emit absorption spectrums. Remember, we had a white light source. It passed through gas, and then you get this absorption spectrum. Okay? Well, we're talking about the sun. I'm going to tell you right now there is no cloud of gas floating in space between the Earth and the sun. So how is it emitting an absorption spectrum? Because you got to have that cloud of gas, right? Okay, so here's the sun. Now, guys, the sun is a star. All stars are made of the same stuff. They're all the same thing, okay? So here's the sun. Stars are not solid. Stars are made of gas. Here's the Earth over here somewhere, okay? The light produced inside of a star is not produced at the surface. Light is produced at the core of a star, okay? So this is where the light's produced, in the core. Now light moves out and away from the core like so. All of this material is gas, and so the light has to pass through the gas. Remember, white light, which is what's being produced in the core, passing through a gas will produce the absorption spectrum. So the absorption spectrum is being produced by the white light at the core being produced passing through the gas that is surrounding it, because this is all gas. Okay? So this is what is the gas cloud that's between us and the sun. It's the sun itself. Okay? Light produced at the core has to pass through the gas that makes up the sun, and then we get the absorption spectrum. Okay? Now let's talk about the Doppler shift. Okay? The Doppler shift can be thought of as sound. Sound travels as waves, just like light does. And in any physics book, any astronomy book, they always talk about it in terms of sound, which is what we're going to do, and then we're going to equate that to light. The reason we can do this is because sound and light both travel as waves, and they behave the same. Okay? It's just one way our ears pick it up, the other way our ears won't pick it up. Again, that's an evolutionary process and sensitivity to the source. Okay? So what is the Doppler shift? Now, let's say you are down downtown Gainesville somewhere, and you're standing at a street corner. So you're standing still, you're not moving, and you're waiting for the light to change so you can get across the street. Now, in the distance, you hear a siren. And as you're standing there, not moving, and you're listening to the siren, it's getting louder and louder. Now, as it's getting louder and louder, the pitch of the siren is going up. Now, as it's getting louder and the pitch of the siren is going up, is that object, that emergency vehicle, coming towards you or away from you? Yes, it's coming towards you. So, remember, it's traveling as a wave. You are standing still. You're the anchor for that sound wave. So, as the object is coming closer to you, the wavelength is getting shorter. As the wavelength gets shorter, the frequency goes up. As the frequency goes up, the energy of the sound wave goes up. Therefore, it's getting louder and the pitch is getting higher. Okay? Now the emergency vehicle is right here in front of you. It's just screaming at you, and then it moves away. Again, you're not moving. You are the anchor for this particular sound wave. So as it's moving away, you'll notice that the sound wave, the wavelength of the sound wave is getting longer. That means the frequency is going down. That means the energy is going down. That means the pitch is going down. That means the object is moving away from you. Okay? Now, what does this have to do with light? We use the Doppler shift in astronomy all the time to tell whether or not, as an example, galaxies are moving away from us or towards us. And we can do that by looking at the light from it, the spectrum of the light coming from the galaxy, okay? So, if we are in our galaxy and we're looking out into space at another galaxy, I can get the spectrum from this galaxy. If the spectrum is shifted into the red end of the spectrum, the red end of the spectrum, that's telling me that the galaxy is moving away. Because if the galaxy is moving away, that means the wavelengths are longer of the light. Therefore, the frequency is lower, the energy is lower. Remember, on my electromagnetic spectrum I showed you, and I told you guys to be aware and ready for this. Red was a lower frequency, violet was a higher frequency, higher wavelength, lower wavelength. So if I'm looking at a red shifted spectrum, that means it's moving away because the wavelengths are longer, the frequency is lower. If I'm looking at a galaxy and the spectrum is shifted into the blue region, that's telling me that it's moving towards me because the blue end of the spectrum is smaller wavelengths, higher frequency, higher energy. Okay? So we can tell by looking at the spectrum and seeing if it's red shifted or blue shifted to tell us whether or not that galaxy or that star or whatever it is we're looking at is coming towards us or moving away from us. Okay, so this is how we use the Doppler shift in astronomy. All right? Okay, looks like we're ready for another break. When we come back, we're going to talk about Telescopes, this is the last thing we're going to talk about in Chapter 3, and I'm going to do telescopes all in one setting. We will not be taking a break once I start talking about telescopes, okay? Yeah, we use telescopes in astronomy. They are a tool that we use. Believe it or not, there are more important tools in astronomy than telescopes. They're not really used all that often anymore. I say that with a grain of salt, but they're not as prevalently used as they used to be. So when we come back from our break, I will be talking about telescopes, and we're going to do that all in one setting. So you guys take a break, stretch out, do whatever you got to do. I will be back to talk about telescopes here in a moment.